actually, this is an initiative to establish a quantum network in the Rio de Janeiro metropolitan area. And what you see here is the backbone of the already existing network for classical communication in, among the scientific institutions in the Rio de Janeiro area. So we see here the Catholic University, the Brazilian Center for Physics Research, the Federal University of Rio de Janeiro, and the State University of Rio de Janeiro, and others, okay? So the main institutions participating in this initiative are those listed here. So the Fluminense Federal University, our university, the Catholic University, the Brazilian Center of Physics Research, the Military Institute of Engineering, and the Federal University of Rio de Janeiro. And these are the funding agencies from different projects and different initiatives, okay? So it involves the CNPq, FAPESP, the Brazilian Minister for Science and Technology and Innovation, the Minister of Defense, the National Institute for Science and Technology and Quantum Information, FINEP, and also the Rio de Janeiro State Funding Agency. So this is a map of the Rio de Janeiro area. What we see here is the Federal University of Rio de Janeiro. This is the entrance of the Guanabara Bay, the Catholic University here. So this is Copacabana and Ipanema beaches. We see here the Brazilian Center of Physics Research, the Military Institute of Engineering that is really nearby. And across the entrance of the bay, we see our university, the Fluminense Federal University. So all these institutions here, these four here, they are connected through optical fibers, okay? So we have received a pair of fibers connecting the Federal University of Rio de Janeiro to the Catholic University, and the Catholic University to the Brazilian Center of Physics Research. And between CBPF and the Military Institute, we have both fiber and free space link, and we also were fortunate, lucky enough, to have a free space link between our university across the bay and the Brazilian Center of Physics Research. So this is a picture taken from our building with the view for the Brazilian Center of Physics Research. So the main idea of a quantum network is to establish a network for distributing quantum states between users that are geographically distant, okay? What is it good for? So we have this example by the Chinese community that they could achieve quantum state transfer over like 1,200 kilometers assisted by prior distributed entanglement, okay? We need this. Why do we need this? There are many applications. One of them is for computing in the network, so distributed quantum computing. Another one is for security reasons, so we can use a network for exchanging quantum key, cryptographic keys, so what is called quantum key distribution, which is protected by physical law. So you cannot, it's a security that does not rely on the complexity of a mathematical function, of inversion of a mathematical function, but it's rather based on fundamental laws of quantum mechanics, okay? So essentially, in the fiber links, what we are going to employ is the protocol that we call the twin field protocol. In this kind of protocol, we have two communicators, Alice and Bob. Where is Bob? Oh, okay, Alice and Bob, okay? So, and actually, so they exchange photons, but these photons, they are modulated in phase by the two agents, and they are measured by a third party that we call Charlie, okay? In this sense, this Charlie, this third party, it can be an untrusted one, okay? Does not be someone that you trust, can be even a eavesdropper, but the point is that Charlie cannot make any kind of transformation on the information encoded or the transformations encoded by Alice and Bob. So in this sense, this kind of protocol is measurement device independent, okay? So let's see a little bit what's the principle of the protocol. So essentially, you have a photon that travels through Alice and Bob lab. It can go one way or the other, okay? Single photon that can go one way or the other, and is going to be measured at Charlie lab, okay? So Alice and Bob, they can perform phase shifts that are like one of four possibilities: 0, pi, pi over 2, and 3 pi over 2, okay? So in this sense, for those who are acquainted to the BB84 protocol, in which you use two orthogonal polarization states that belong to two different mutually unbiased bases, okay? In this sense, 0 and pi, they play the role of two orthogonal states of a given basis, and pi over 2 and 3 pi over 2 play the role of the orthogonal states of a mutually unbiased basis, which means that if Alice and Bob, they perform phase shifts that belong to the same set, the same phase basis, okay, the result at Charlie output of Charlie's measurement is deterministic, in the sense that it's 100% one port, 0% the other port. Which port will be depends whether they put the same phase or different phases. However, if they implement phase shifts that belong to different bases, then the outcome of Charlie's measurement is completely random, 50-50%, okay? So from this point on, it works pretty much like the BB84 protocol. So essentially, there is a stream of photons that is sent from from Alice and Bob to Charlie, and they perform their phase shifts. Every time, then they publicly announce the basis choice that they made, not the result, not the phase shift that they made, but only the basis choice that they took. And also, Charlie will announce his result, his detection result. So only with these informations, Alice and Bob can infer the transformation made by the other one every time they chose the same basis and according to Charlie's result, okay? So this is the logic of this twin field protocol. Now, so this is essentially the kind of protocol that we are going to implement in the fiber connections, okay? So this was a proposal of Guilherme Temporão to use this kind of protocol, and he's the specialist in this kind of system. Now, we are more, at the Fluminense Federal University, we are more working on the free space link. And for the free space link, at the first moment, it will be very difficult to implement the twin field protocol. So what we will start to do is to make investigations on the use of structured light for quantum communications, for free space quantum communications, which is a quite hot field at the moment with many, many different developments. So essentially, this structured light issue starts with encoding information on the spatial structure of a photon. So you can prepare a laser beam in any of different possibilities of spatial modes. These spatial modes, they appear naturally from theoretical background as solutions of the wave equation in paraxial approximation. So this is the wave equation that describes a well-collimated beam, like this laser pointer here. And for the solutions of these equations, we have not only the Gaussian solution, that is usually how the lasers are built to emit a Gaussian mode. However, we can engineer not only the laser cavity if we want, but after the laser cavity, we can engineer holograms or any kinds of boundary conditions that allow us to produce any transverse mode that is a solution of this paraxial equation. Okay? And we can do this in the lab with spatial light modulators, with digital mirror devices, and other holographic structures. So essentially, for example, each family of modes here is presented in a hierarchy of orders. So these are the Hermite-Gauss modes, which are essentially the product of Hermite polynomials and Gaussian functions. These are Laguerre-Gauss modes that are Laguerre polynomials and Gaussian functions. However, these Laguerre-Gauss modes, they also have some phase modulation, spatial phase modulations that give them a twist in the wavefront. So it makes them like orbital angular momentum carriers. So besides the angular momentum carried by a light beam in the polarization, the circular polarization, it can carry also angular momentum in the spatial mode. And you can encode, you can use that to encode information. You can create qubits encoded in this kind of degree of freedom. Now, one example of structured light application to quantum communication is comes up when you combine this spatial degree of freedom with the polarization. So if you combine polarization and spatial degree of freedom, you can have this kind of mode structure here, in which these are modes in which the polarization state is not uniform over the wavefront, but it varies point to point, okay, from one point to another. So these are radial polarization. So at each point of the beam, the polarization points radially, okay? And this one is azimuthal polarization. They are orthogonal modes, okay? These two modes they are orthogonal. And also, we can define a mutually unbiased basis by simply combining them with a plus and minus sign. And the interesting thing here is that since these two modes are rotationally invariant, so we can do math to show that, or we can just look at the pictures. We see very clearly that if we rotate these two pictures, they remain the same, okay? So these two modes here, they are rotationally invariant, so any linear combination of them is also rotationally invariant. So this allows us to implement the BB84 protocol without the need of aligning the two stations. So one problem in using the BB84 is that Alice and Bob, they must agree with respect to what they call horizontal and vertical plus 45 minus 45. In this case, you don't need that. Okay? Even if the two labs are misaligned, they can implement the BB84 protocol. So this is one clear advantage that you get from combining this kind of spatial mode encoding with polarization encoding, okay? Another problem is that now suppose that I want to increase the space of modes, the alphabet, the space that I use to encode the cryptographic alphabet, not only to restrict to qubits, but go to Q-trits, Q-quarts, and so on. So this spatial structure also allow me to make superpositions of modes, different spatial modes, okay? So it's not like polarization that has dimension 2. It can have arbitrary dimension. But the problem is, how can I do tomography, or how can I measure a quantum state prepared in this degree of freedom? So this is the main problem. Now, we know that for doing tomography in polarization, we need to do quantum state tomography. We need to make measurements in a set of mutually unbiased bases. So the set of mutually unbiased bases grows, the number of mutually unbiased bases grows with the square of the dimension. So, like, it's unnecessary to explain much about the difficulty that appears as you raise the dimension of the space that you are using to encode information. So we have dealing with that, with encoding qubits in mode, in this mode space. And the problem that we tried to solve, that we solved, was suppose that we prepare a superposition of, let's say, five modes. So I'm working with a space with dimension 5. And I want to be able to build or to reconstruct the quantum state only from intensity measurements with the camera, for example. I'm not going to do measurements with not POVMs, I will use always, but not with mutually unbiased bases, not the usual POVMs used for quantum tomography, but only intensity measurements, okay? So one problem that appears when we try to do that is that if we look at the intensity distribution of a beam carrying angular momentum in the spatial domain, okay? A beam that is right-handed and one that is left-handed, they have the same intensity distribution. So obviously, I cannot distinguish them only from intensity measurement. However, if I do an astigmatic transformation, and this can be experimentally very easily done, for example, if I image the beams with a spherical lens, I just have the plane image, but if I tilt the spherical lens, okay, by a convenient angle, I don't need to explain how we calculate this angle. Actually, in the lab, we just do it empirically, okay? It depends on the characteristic of the lenses and everything, but we do it empirically. We know, but we can, like, calibrate this tilt angle to a given angle in which, close to the focal plane of the lens, these two different helicity modes, okay, they are transformed to Hermite-Gaussian, orthogonal Hermite-Gaussian patterns. And then these transformed patterns can be recognized only from intensity measurements. Okay? So this raises the degeneracy or the ambiguity that we had in the start. So in a first experiment we used machine, we made superpositions of different orders, okay, different modes, all of the same order, but different modes, okay? And we could recognize them using machine learning only with the two measurements. We would train the machine by feeding images of random superpositions, okay? But not only the direct image and the astigmatic image, the one that is transformed by the tilted lens. By feeding the machine with the pairs of images, the machine could learn how to recognize any kind of superposition, okay? And only with these two measurements, with these two intensity measurements, we could reconstruct the quantum state, the superposition that were being encoded in the beam, without the use of mutually unbiased bases for dimension 5, for example, that would go like, would be of the order of 25 different operators, okay? So this is a considerable gain. At that time, we showed this work in the conference at Paraty, the Quantum Information Conference, and the theorists present there, they said, okay, but you must demonstrate that this kind of measurement is informationally complete. We only had this empirical demonstration that, okay, if the machine succeed in determining the superposition, it must be informationally complete. It could not do that by chance, just by luck, okay? But it's true that at that time, we didn't have a formal demonstration. Now, we solved this problem, and we have a formal demonstration that actually this kind of measurement is not, so with the machine learning, we only used coherent superpositions. We didn't work with mixed states, but now we have the demonstration that the method is useful for all kinds of states, mixed, pure states, it doesn't matter, and to any dimension, okay? Only 2 images. So this is the kind of thing that we are right now, we are setting up the free space link, the free space link between the UFF and the Brazilian Center of Physics Research is like almost 7 kilometers long. It's 6.8 kilometers, okay? And we are setting the telescopes to send the superpositions across the bay and make the identification on the other side using our technique of this double intensity measurement, okay? So essentially, I showed you just, it was just to give you an overview of the kind of research that we are doing there. We are trying not to make the Quantum Rio Network only infrastructure, how can I say, setting, but also a test bed for scientific and technological investigation, okay? So in conclusion, what we have done is this, setup of a functional quantum key distribution network among the partners institution, and development of our own technology. So the idea here is not just to buy stuff and like implement them in a network in the Rio de Janeiro area. It's more than this. We are scientists. We want to do science. We want to develop new concepts, new methods, new protocols, and also, if it happens, new devices for quantum key distribution and quantum information protocols in general. Of course, this network has promoted an interesting synergy between the institutions in the Rio de Janeiro area, okay? So people are starting to talk a lot about common projects, common scientific projects, okay, that can be done. So we have, for example, an ion trap built at the Federal University of Rio de Janeiro. We have nanoparticles trap at the Catholic University. We have NV centers at the Brazilian Center of Physics Research. We have photon pairs generations at UFF, at the Federal University of Rio de Janeiro, and at the Catholic University as well. We are going to have it also at the Brazilian Center of Physics Research soon. So we have all the proper environment for a scientific development within the context of this quantum network, okay? Also, of course, this infrastructure that we are building can serve as a test bed for companies, government institutions, scientific institutions from other states in Brazil, from other countries in the world, it doesn't matter, okay? Of course, in the future, when this network is in operation, we can think about integration with other initiatives, for example, the one in Recife, the one in São Paulo, okay? But we all, as in other communities in Brazil, we have these challenges to face. Attract more people, we need labor hand. We need young labor hand, young people motivated to take part in, how can I say, in an important project. And also attract companies and the startups to work with us. So these are the people involved. Of course, there are many more people, but let's say these are the ones that are taking in charge of all the responsibilities in the different institutions. So I am at the Fluminense Federal University, Guilherme Temporão at the Catholic University, Vitor Andreso at the Military Institute of Engineers. Now, Rodrigo Sacramento is at the Federal University of Rio de Janeiro. He's running the ion trap lab. They already have a working ion trap over there. And at the Brazilian Center of Physics Research, we have these 4 members here. We have Ivan Oliveira, who is leading a project to make superconducting chips for quantum computation. Fernando de Mello is a theorist that is also working on the security issues of the protocols that are going to be used in the network. Newton Alves is a technician from the Brazilian Center of Physics Research, and he's our contact in the Rio network, okay, in the classical network, okay. So he's the guy who opens the gates for us, okay. And Gabriel Aguilar is the last acquisition. He was formerly at the Federal University of Rio de Janeiro. He now moved to the Brazilian Center of Physics Research, and he's now setting up a new quantum optics lab over there. And with that, I thank you for your attention.
Thank you very much. I'd like to ask, see if there are any questions from the audience. There you are.
So thank Zelaquett for your nice talk. And I would like to know how resistant are your state to the weather condition?
Yeah, so this, we haven't characterized the channel yet, but this is why this identification, this recognition system that we have is so important. We will be able to evaluate that by measuring the fidelity of the detected mode on the other side with respect to the one that we prepared, we intended to prepare. And then we will see. So you see, from my intuition is that, of course, it will vary a lot along the year. And right now, this season, the autumn season, is a season of the best weather conditions that we have, okay? Even by looking at the telescope, we see the building in details and everything very, very... So I believe that we can achieve rather good fidelities at this season. In the summer, forget it.
Other questions?
I actually have 2 small questions. First, you said that you can transform your Gauss modes into Hermite-Gauss modes with the astigmatic transformation.
Yeah.
Are these transformations reversible? So can you make the other way around?
Yes.
Okay.
Yes.
So that was the first one.
You can do that.
And the second is...
It's unitary. So you and you, Dagger.
And the second one is, you're using telescopes to make the connection between the 2 points. But why use the telescopes? Like, what the increase of the diameter is good for? Or why can't you order some kind of lenses that has just a really far away focus? So you can, like, if you have a 10-kilometer wave, you have a 10-kilometer focus lens, so that you can focus on the other side of the...
I'm not sure I understood the end of your question, but let me see if I can guess. So you are worried about technical problems related to, first, what is the focal length of the lenses that we use, and also the beam, of course, it will expand, and we won't be able to collect it all, okay? This is true. However, this image information is a lot of information, and actually it has a lot of redundant information. So we also, when in our work, demonstrated the informational completeness of the method. We also tested for blocked beams. Okay, so we made a study on about how much we can block of the beam and still be able to reconstruct the original state that we prepared. Okay, and actually, if we detect at least 50%, even a bit less percent of the beam, we can have fidelities as high as 95%. Okay, so this will be like, we have to work from two fronts. We have to optimize our collection, beam collection, and we also have to work on the algorithm for recognition. We are working on both sides, on both fronts.
And do you have many power losses in the way? So do you need to have like a high intensity beam?
Power losses, yeah, we have, the power losses in principle should be of the order of 50%. Well, only absorption, okay, not spatial losses due to the aperture of the telescope.
Thanks.
Okay, thank you very much. So, any other questions from the audience? Otherwise, we're quite late now, so I'd like to thank Zelaquett again. And then pass the floor to Professor Filippo Gigliano. Oops, quite entangled.
Peraí. Vamos fazer aqui.
Mais fácil.
Bom, primeiro é este. Tem que ligar aqui em cima. Aqui em cima tem um botão para você ligar. Sim, esse aqui. Aqui.
Okay, meanwhile, just a brief remark. There's a list passing. I would like to ask all of you to sign it, everybody in the audience to sign it. Those who have not the name on the list can sign on the second list in the back. It will be left here for anybody who has not signed it yet, can sign it during lunchtime. So, with no further delay, I would like to leave you with Professor Filippo Gigliano from Federal University of São Carlos. Just a moment. Vai? Sure. Let's see if it's sharing now.
Let me try the pointer.
Sure.
Okay. Yeah. But